Hey everyone, and welcome to my VHDL guide. In this video I will be going through the necessary steps for getting VHDL up and running on your system. We will conclude this guide by designing a simple logic circuit and simulating it. All the links, code and commands that I used in this guide are listed in the description below. However, I highly recommend that you follow along and type everything yourself. It will really help you out in the long run. I do want to point out this guide is specifically for Linux. If you are on a Windows machine, click here to check out my Windows version of this guide instead. So, let's get started. The two programs you will need for this guide is GHDL, which is our VHDL compiler and simulator, and GTKWave, which is our waveform viewer. GTKWave is part of the GEDA software suite, which incorporates a number of other EDA tools. However, we won't be touching any of the other ones in this guide. You can check out my other videos that talk about them if you're interested. So let's go ahead and install GHDL and GTKWave. I'm currently running Fedora 24. If you're using Fedora 22 and up, you'll be using the same command as I do, which is su-c, and we want to install, so dnf-y, install, and then GHDL and GTKWave. If you're using Fedora 22 and up, this is the command you will be using. And let me type my password quick, and it will be installing. Now, if you're using Fedora 21 and below, you'll be typing the same command, but it will be su-c, and you'll be using yum install GHDL GTKWave instead of DNF. So that's the command you'll be using if you're using Fedora 21 and below. If you're using a different Linux distro that uses a different package manager such as Ubuntu, you'll be using a similar command, but it would be sudo, and then it will be sudo, and then you want apt-get install, and then you'll be specifying the GHDL and GTKWave. So whichever distro you're using, that's the command that you'll be using. So let's go ahead and install it. Now that we have everything installed, we want to write some code. But before we actually write any VHDL code, I want to create a working directory for my code and any generated files that will be created as we go along. So I'm going to go to my home directory, and then I'm going to create in there a directory that I'm going to call HA for half adder. You can create that directory wherever you usually write your code, and then I'm going to cd to my half adder directory. Using your favorite source code editor, let's create the half adder VHDL code. I'm going to use Vim, so let me just create another command prompt window so you can see clearly over there. I'm going to create the file using Vim, so I'm going to go Vim ha.vhdl, so that's our half-adder.vhdl. You can use Nano or any other source code editor that you like, and so let me go ahead and start it. The first thing we want to write, of course, is that we're using the IEEE library, and from the IEEE library we're going to use the IEEE standard logic signals 1164.all, and that tells it that we want to use the package that deals with that gives us all the standard signals that we'll be using. And we want to create and let's go ahead and start an entity block, and we're going to call it HA for half adder is, and we're going to close the entity block by ent HA, And inside the entity block, we're going to write a port clause. And what the port clause does, is it gives us the signature for our block as seen from the outside world, which in our case is going to have one input in, and it's going to be a single bit STDU logic, and we're going to have another input B, and it's also a single bit STDU logic, and then we have O, which is going to be our output, and it also a single bit U logic, and finally we have a C carryout, which is also STDU logic. So what we have here is we have two inputs, A and B, for half adder, and then we have two outputs, which is our sum and our carryout. So let's go ahead and describe the architecture for, and then I'm going to call it behave, of HA for half adder is, and then we always start the block with begin, and then we end behave. And inside the architecture block, we actually describe how our entity, how do the signals flow. So in our case, since this is just a simple half adder, our output is 1 when either A is 1 or B is 1, but not when both. So for example, 0 plus 1 is going to be a 1. 1 plus 0 is going to be a 1, and 0 plus 0 is going to be a 0. So we want it when A is 1 or B, but not both. So that would be A XOR B. And our carryout, C, occurs only when it's both A and B. So not when either one, but when both of them. So it's going to be A and B. And I'm going to go ahead and save the file. And before we move on, I want to check out that I did not make any kind of a syntax error in my code. So to do that, I'm going to go ahead and I'm going to invoke our GHDL compiler. So I'm going to type GHDL, and I'm going to use the -s switch, which does a syntax check only without compiling anything. So I'm going to do -s, and I'm going to give it our half-adder.vhdl file, and I'm going to hit enter. Now if we don't get any messages, then we know we're good to go. Unfortunately, you'll see that I have made a syntax error, and it told me that on line 11 on 1 we're missing a semicolon at the end of our port clause, and indeed here at the end of our port clause we are missing a semicolon. So I'm gonna go ahead and add a semicolon, and I'm gonna save the file again, and then I'm going to run the GHDL compiler -s command again, and notice that this time we have no syntax errors, so we know that this file, at least syntactically, is correct. We have not proven that the logic is correct, but at least syntax-wise it's correct. Now that we have our half-adder code complete and we know that it is syntactically correct, we want to prove that it's also logically correct, because we have not proven that yet. To do that, we're going to create something called a test bench. So let's close this file, and I'm going to create another file, and I'm going to call it HA for half-adder _ TB.vhdl, and TB stands for test bench. And then I'm going to start out with the same way, library, and we're going to tell her we want the IEEE library, and we want to use the IEEE standard logic 1164.all, and we're going to create an entity which we're going to call HA _ TB. Now this is the traditional naming convention that is used for naming test benches, which is the name of the unit under test. This is called UUT, or the unit under test, followed by an underscore, followed by TB. Later on, or if you've already discovered, there are a number of large, sophisticated, integrated development environments over there offered by the various FPGA companies such as Altera and Xilinx. And in their programs, you can actually semi-generate the test benches automatically, and they follow the very same naming convention as I do here, which is the unit under test followed by underscore followed by TB. So let's go ahead and continue with our entity block, and we're going to write is, and we're going to close the entity block by writing end half adder TB. And you'll notice that the entity block is empty. That is, it has no inputs going into it and no outputs going out of it. And the reason for this should be quite clear to you, because this is a complete unit on its own that is going to generate signals to our half adder, and it's going to read the output signals from our half adder back, and it's going to check that it is logically sound. And because of that, we do not expect any signals coming into our test bench or going out of it. So it's going to be empty. However, we need to actually write the code to conduct our test. So let's go ahead and describe the architecture of our test bench. So we want architecture, I can't spell, and we're going to call it test of half adder.t underscore TB is, and we close the architecture block by writing end test. And inside the architecture block, we're going to tell VHDL that we are going to use a half adder component, so component HA, and we end the component block, component, and inside the component we have our port, which what I usually do is I usually copy the port directly from our entity block. So I normally copy it verbatim. The reason I do that is because they have to match. And if I copy it verbatim, then I know it matches 100% and I did not make any errors. Many people make a lot of errors in this specific part. So if you get an error, such as something is not bound correctly, this is probably why, because your component doesn't match the entity block. So I copied that verbatim in here, and so I know that this matches exactly. And now I'm gonna describe a number of signals. So I'm gonna create a signal for each input and each output. So I'm just gonna name them the same thing as in our half adder. So I'm gonna name them A, B, O, and C, and they are all STDU logic, so they are all single bit signals. And let's start the architecture itself. So we're gonna type begin, and we're going to create a port map, and we're gonna call it half adder, and we're using the HA entity, HA component, and then we open a port map, and we're simply connecting our signal A to the A input of our component, of our half adder, and we're connecting our B signal with the B input of our half adder. We're connecting our O signal to the output of our half adder O, and likewise we're going to connect the C signal to the carry out of from our half adder as well. There you go. And now we want to write the actual test to see that our logic is correct. So to do that, we're going to create a process, and the reason we're creating a process is because we want to run everything sequentially. So we're going to say process begin, and then we close the process block by typing end process. And inside our process block, we're gonna start with our first test. So in our first test, I'm going to actually give both inputs a strong unknown. So I'm gonna start out with both A and B having an unknown signal sent to them, and I'm gonna wait for, we're going to wait for 1 nanosecond. For 1 nanosecond. And after we wait that 1 nanosecond, we're going to give A 0, and we're going to give B 0 as well. So the first test I'm writing will check what happens when I add 0 plus 0. And of course, the end result should be a carry out of 0 and a sum of 0. And then we want to wait for 1 nanosecond. And then we'll write another test, which is this time 0 for A and 1 for B. And we're going to wait for 1 nanosecond again. And then we're going to have 1 for A and 0 for B. And we're going to wait for 1 nanosecond as well. And finally, let's just make this a little bigger so you can see the entire code. And finally, we're going to have A is 1 and B is also 1. And we're going to wait for 1 nanosecond, and after we wait that, I'm going to write a simple assert statement which is going to evaluate, and I'm going to print a message that says reached end of test. And then we have to put a final wait, and notice that I did not specify time, and that will tell the simulation that I'm waiting forever, effectively ending a test bench. So I'm going to save this file, and I want to point out that practical test benches will not look exactly like this. They will probably have lots of if statements and lots of conditional checks, and they will go through exhaustively checking all the signals, and they will also be checking the output signals. Note that in our test bench, I did not do anything with our O and C signals, and the reason for this is because the half adder is so simple, we can just test it using the Waveform viewer that we've installed earlier. In real practical test benches, you will have much more code here, a lot more assert statements, and they will be checking everything exhaustively. So now that we finish our test bench, I'm going to first run the GHDL-S _TB, and I'm going to just syntax test my test bench. So notice that there are no error messages, so I know that at least syntactically my test bench is good to go. And what I'm going to do now is I'm actually going to analyze our half adder, and to do that we're going to use the -A switch, and we're going to specify the half adder.vhdl file, and we'll let it execute. Once again, if there are no problems, you'll see no messages, so in my case I'm good to go. And I'm going to also analyze the test bench file. So we're going to use the -A switch again for our test bench, and once again no messages, so we're good to go. And I'm going to tell it we want to analyze, the -E stands for elaborate, so we want to actually build the simulation for our test bench. So the way we do that is we do GHDL-E to elaborate, and then in here we tell it which object we want to actually build. And in our case, it's the half adder HA_TB. Notice that we don't specify file, so there's no file extension, but we're giving it the unit we want to elaborate, which is a half adder, which is effectively this entity we're trying to test. So I'm going to hit enter, and it compiled it. And once again, if there are no error messages, you're good to go. And now we want to actually run our test bench. So to do that, I'm going to do GHDL-R, and then once again, I give it the name of our object, which is a half adder test bench. And you'll see that it ran, and it did print something. However, it is not an error message. It's actually our assertion error that we have created, which was reached end of test. That is, it went through all of these tests and it made it here, which evaluated false, and which is why it printed this out. So this is good news. It told us that our test bench ran through and executed. However, we actually want to check out our waveform diagram. So to do that, we'll create something called a VCD file. And to do that, we specify --VCD equals, and then we tell it the name of the file we want to dump our time values into, which is halfadder.vcd. And I'm going to hit enter, and notice that the simulation ran once again, and it executed my code, and it printed the assert statement once again. But this time, if I check the listing of my directory, you'll notice that I have generated a halfadder.vcd file. With our VCD file generated, let's go ahead and inspect it. So VCD stands for value change dump, and it is a dump of all the signals and their values that have changed during our simulation. So to view it, we'll type GTKWave, and then we'll give it our half-adder, so HA.vcd file. And this will open up our GTKWave program, which is a waveform viewer. And let's make this a little bigger. And you'll see on the upper left corner, you have our half-adder. And we want to drag to our signals interface the signals that we want to check out, which in our case is actually all of them. So we want A and B, our inputs, the sum, and the carry out. And you'll see that our units actually starts with femtoseconds, which are 10 to the negative 15 of a second. So this is a very, very, very small. It's a 1 quadrillionth of a second. So this is a very small unit. And we've defined our test in terms of nanoseconds. So this is way too small for us. So the way you zoom out is you hold down the control on your keyboard, and then you can use the scroll wheel to scroll up and down and zoom in and out. So I'm going to scroll out, and now we are in picoseconds, which is still too small, so I'm going to continue to zoom out, and there we go. So I zoomed out to nanoseconds, and now you can see our signal changing. So you notice that between 0 and 1 nanosecond, we told our test to give A and B a strong unknown signal, and therefore the output is irrelevant for us because it is unknown. The input and output the inputs are unknown. So let's go ahead and check our first actual test, and that is between 1 nanosecond and 2 nanoseconds. We gave our half-adder 2 inputs which are both 0. So we're telling it add 0 plus 0, and we get an output of 0 and a carryout of 0. So the logic for 0 plus 0 is correct. Now between 2 nanoseconds and 3 nanoseconds, we told it to add 0 plus 1. And 0 plus 1 is 1, and it has no carryout, so carryout of 0. So this is correct again. Between 3 nanoseconds and 4 nanoseconds, we gave it an input for A of 1 and B of 0. And once again, 1 plus 0 is 1 with a carryout of 0. And finally, between 4 and 5 nanoseconds, we gave it an input of 1 for A and 1 for B. And the sum of 1 plus 1 is 0, and we do have a carryout this time. So the logic for our half adder, so if I close this and I go back to a half adder, and edit anyway. So the logic for a half adder is sound. This is it for this guide. I hope you were successful in following along and getting everything to work correctly. If you got stuck on anything or you have any comments or questions, do leave a comment below. I will try my best to answer them. If you're interested in additional guides, please check out my other videos in my channel and don't forget to like and subscribe. So thank you.